Okay, we made it to the end. Last lecture of content. We'll do a review, we'll do a test, we'll do a tour. It's going to be a great end to a semester, and then we'll kick you guys out of here. Go do something in the world. Make us proud, which I'm sure you will. Most of you are seniors, yeah. So if you're not, don't feel bad. Okay. And so today we're going to talk about particle characterization because that's one other physical property that's really not talked about much. And you'll see there's a couple of figures in here that are pretty dramatic in terms of what the particle distribution can tell you. But this is really, I don't know that there are even any questions on the homework on this. It's really just sort of to round out the last thing. We've talked about fibers, we've talked about polymers, we've talked about like the physical properties of powders and so on with color. This again a physical property, but now we're talking about the size of the particles, and there's a lot of information that can be gained from that. So you could have two powders that have the same chemical structure, and we'll see that today, and based on the way they were prepared, you'll see dramatically different particle shapes and sizes. We call it morphology. So let's jump in. So these are some of the physical properties in particle samples. So when you have a powder, you've got a range of particles. You have a size distribution. So you've got every one of those little particles has a slightly different diameter, and so you'll get some kind of distribution of diameters in that powder. Or it could be some are long and skinny, others are more like gravel, and so we'll see some of those examples today. Length to width ratio. So that's another way to characterize the particles. Then you can have equivalent spheres, and we'll talk about what that looks like today. Particle volume or surface area. We talk about surface area in terms of per unit mass. So how many square meters of surface are there per gram or per kilogram? And so there's ways to determine that. There's this BET isotherm analysis where you put the particle in a little chamber and you cool it down, and then you condense argon on it, and then you measure the ideal gas law, the pressure, temperature, volume relationships of argon, and it's not what you'd expect, right? You put argon in a cold temperature, you would expect it to have a certain pressure and a certain volume. You're looking at that isotherm, and it's not what you'd expect. Why? Well, because the argon molecules or atoms have adhered to the surface of your particle. Okay, so you're missing some moles of gas. And because you're missing some moles of gas, you can calculate how many moles of argon are on the surface of your particles. And so that's a short version of what the BET isotherm analysis is. So you cool it down, and the gas molecules adhere to the surface, and so they're not in the gas phase. And so then you can calculate how many moles of argon it took to cover your particles, and that way you can get the surface area of your particles. So it's a pretty common analysis. It's a little technical, but you can have instruments that do that for you. And then you can get down into the microscopy and look at the shape of the molecule, whether they're spheres or rods or plates, whether they're crystalline or amorphous. So there's lots of different physical properties of particles, and today we're going to talk about how to measure those. Now the bulk, like large particles, like let's say you have a mud on a boot, okay, and so that's your questioned article. You can scrape off that mud, and then you could do a sieve analysis and see what the particle size distribution is of that mud, whether it's a clay or a silty soil. And then you could go to a scene. You've got maybe an imprint, but you want to verify that yes, this is the exact same soil or silt or clay that's on the questioned item. You take a sample, you could do a sieve analysis on the known and see if they match. They could match chemically. It's the same kind of clay, it's the same kind of silicate soil, but if it's a different particle distribution, then you've got a differentiation. And so this is the sieves. And pass these two around. I've only brought two, but you have a whole stack that you typically buy as a kit. Look on the side here. It says, let me see what it says. Yeah, it says aperture. So the aperture or the size, the hole in this mesh is 75 microns, and this one is 500 microns. So I got two at the extremes so that you could see the difference between them. And so I'll pass these around, and you can see this one, it just looks like a film, but it's actually a wire mesh, a steel wire mesh and so here. You can look on the side to see their stuff. So you put the sample up here in the top, in this top sieve, and it would be the smallest. Let's see, let me make sure. No, the more coarse would be at the top one. So the largest holes are in the top, and so you wash that, and it goes through the biggest hole, and then the next one has smaller holes, and so then that traps a little bit more, and then the rest falls down, and then the next one traps, and so you have all of these different sieves, and so you would calculate the percent passing on these sieves, and so if 80% passed the big sieve and then 60% passed the next sieve and so on, then you could plot out the cumulative or the integral of the particle distribution curve, and we'll see those in a second. Now it's difficult, surprisingly, to get, let's say you have a muddy sample in that top sieve, to get it all to go through. I mean, you'll have some big, what I call pickers, some big rocks in there. Those will obviously be trapped by that top sieve. But then you have the particles that get kind of close to that sieve, and they're all adhered together and so on. So you've got to wash them, and you got to tap the sieve so that if the particle doesn't quite line up, but then you tap it and it lines up and goes through, then we want that to happen. And then you also, all the mud or sample gets off to the one side of the sieve, so you got to rotate the sieve. It's incredibly tedious to try to do this by hand. So they make sieves shake, rattle, and rollers is what I call them. They spin the sieves, they vibrate the sieves, they thump them, and then they have the water going through and passing it through. So is probably the loudest thing that we had in the lab at Pantex doing explosive particle analysis was this thing in the hood, because it's sitting there and it's rocking the whole stack of sieves, and there's really a thing that's just tapping the bottom like what you would do with your fingers. It was like two metal plates with rubber tips on the end. It was like ping, 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 rattle, 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 and the water's going and so on, passing the particles through. But then you weigh each one of those sieves beforehand when it's nice and dry, and then you do the sieving, and then you dry them out, and then you weigh them with the particles on there, and you look at the mass difference. So then you would calculate the mass that passes through. And this is what you get. So if you had sieves at these different levels, like let's say you had a 20 millimeter sieve mesh, and you got this data point, and it came in at like 96% passing. So you see, that's what that data point would be. So you've got you weigh out the total sample that you dumped in the top, okay, and 96% of that mass went through that first sieve. So here's your data point for the first sieve, and then the second sieve is a 6 millimeter sieve, and 85% of that total mass went through the second sieve, okay, and then the third sieve is at 2 millimeters, and 50% of the mass went through that one, okay, and then the last one would be 0.63 millimeter sieve, and 12% of the mass went through that one. So it captured a lot of it, okay? Only 12% went through. And then the last one at 0.2%, it didn't, it's like almost nothing went through that one. So it caught the last little bit. You add up all of those amounts, and you get the total mass of the particles that you started with. And so then you have this smooth curve that goes through those data points, and you would classify that as gravel sand. So it's got some chunks, some big pickers in there, and then it's got down here in the sand region, it's got some sand in it. Now we had, I have to say this just because we had a technician that totally wrecked this behavior, okay? And what they were doing is in the top sieve, they were trying to analyze the powders, right? It's an explosive powder. And in the top, on the top sieve, there were some like really big chunks, what I call pickers, and they picked those out with tweezers because they were focused on the powder, okay? Don't pick out the pickers, right? Leave those in there. That's part of that most coarse thing. Those are the rocks and the gravel that's part of the mass. You don't pick out any of the mass, and our numbers just weren't working right. You know, we weren't getting 100% or something was missing. And we thought, man, is our sieve leaking? Is it spilling out? What's going on? We looked at the equipment. And so the only way to diagnose something like that is what they call walk the line. It's like a production line. You know, if you're a manager, you go walk the line and say, show me how you do this analysis. Okay. And so this person was saying, okay, I pour it in, I weigh it, you know, dry it, weigh it, pour it in the top, okay, and I pick out the big pieces because they're not the powder, right? And the guy was like, ding, we know now what's going on. You were pulling out the pickers. Don't do that. Leave the pickers in there. That's that top sieve that's going to capture those big pieces, okay? And so that was interesting. Then you could see if you have these, you know, sand, let's say we've got less or fine sand, you know, let's look at fine sand here. Again, if we had all of these, we still had the 20 millimeter, the 6, the 2, the 0.63, 100% passed all of these. So these still have data points, right? So we weigh the mass, we put it in that top one, we start shaking and rattling and rolling, and the liquid's passing them through, and we dry them and weigh them, and they have the same mass. So 100% of our particles went through those top ones. But then we get to this one, 0.2 millimeters, and all of a sudden now we start to see some captured mass. So we weigh that, we calculate what percentage of the whole, and it looks like 94% passed the 0.2 millimeter sieve. And then weigh the next one, the 0.06 millimeter sieve, captured everything except 10%. So we went from 94% passing to 10% passing. So we've got a really steep distribution here. And then the 0.2 captured whatever was left, so 0% passing. So we only had 3 sieves that captured any kind of the particles, any kind of the material, the sand. And so that would be a very, what we call, you know, it's not bimodal. It's just a single mode. It's a very uniform distribution, and you can always look to see where the 50 percentile is. So 50% passing would be somewhere between 0.2 and 0.06. Okay, so where it crosses this line, that would be what we would call the average particle size. Okay, so this sand is telling us the average particle size is between 0.06 and 0.2 millimeters. The gravel, the average particle size is 2 millimeters. And so where that distribution passes the 50% mark, that's the average. Half is above, half is below. Okay. Now this I don't know if this is a typo or if I'm just not a geologist, but clay, I don't know what clay is. But anyway, clay, gravel, and sand. So this is multimodal. Why do we say that? Well, because it's got this little steep portion here, and it's got a little steep portion here. So remember, this is the integral of a distribution. So if we take the derivative where it's steep, you've got a high slope, and then it comes back down, and then it's steep again over here. Right? So this dotted line would be the integral of this curve here. And so we see multimodal. We see an area where there's some small particles, the clay part, and an area where there's some gravel. And so if you see that percent passing curve, the cumulative distribution they call it, with a couple of slopes that are steep, then you know you have a multimodal distribution. Now, when we get down into the micron region, it's real hard to use sieves. Those particles are really small, they're also really light, and it's just a little bit more difficult to manage. So we start shifting over to other kinds of particle counting and characterization techniques. And when we get to the nanoparticles, we have to use light scattering. We can't use gravimetric anymore. Those particles are just too small. And so let's look at some of the other ways to measure this. So laser diffraction or light scattering, you can have the particles flow down, so you've got some sort of waterfall here, or liquid where the particles are up here and then they fall down in a stream, and they fall in front of the optics, and the laser light hits them and scatters off at some angle. And so you can see by the different sizes of the particles, you'll get different signals at these scattering angles. And so that's a way to measure the cumulative distribution and so you can see here this 90% passing is here, here's the average, and here's the 10% passing. But notice you got some steep areas here and here, and so this is a bimodal distribution. If we take the derivative of that cumulative distribution, we see we have a mode here and a mode here. Remember, the mode is the top of that peak, the most probable for that little sub-distribution. And so this would be a bimodal distribution. This is one where we talked about, let's see, I guess it was in slide 2. This equivalent sphere diameter. So this is treating the particles as a sphere, okay, even if they're not. So like maybe they're oblong shaped or something like that, but they pass through this, and this electrozone equipment measures the particles. So it's got a little voltage put through this salt solution, so electrolyte. And so it can set up a little bit of a potential here, and then you've got this this non-conductive barrier, this insulator, and the particles pass through, and when they get into those holes, they sort of create a resistor based on the size of the particle. So the current changes. So you got a current of ions going through, and ions are really small. You know, cations, anions, they're both going through this passage. If a big old fat particle gets in there and slows down the flow of ions, you can detect it. And now it's pretty complicated, the behavior of that particle in this pore. It's simplified by just assuming the particle is a sphere. So you got a big long needle passing through there. It's going to be really hard to determine if that's a needle or a sphere or whatever. So the assumption is it's just a sphere, and so we'll get the effective spherical diameter of that particle, even if it's a needle. Okay, so you probably want to look at it with a microscope to see what your particles actually look like if you're doing electrozone analysis. But anyway, this gives us an idea, and it's a pretty fast technique. You can sprinkle your particles in there. The current will typically carry them through the hole, and you'll see, you know, a distribution come out of this equipment. Here's another cascade system. Again, you've got your sample flowing through this narrow flow cell, and here you're using microscopy or a camera to image the particles. And so this thing can count 10,000 particles per minute or greater, which is pretty amazing. So they call it machine vision. You have the camera looking at these particles. Typically they want some sort of contrast. They want like black particles on a white background. So they got a bright light aimed right at the camera, and these particles come through and cast shadows on the camera, and the computer can quickly find the particles. The trick to all of these techniques is getting good dispersion. You don't want particles in front of each other. You don't want too many of them that the camera can't keep up. But the camera is pretty fast, or the computer that's watching the camera is pretty fast, and it can determine the shape and the size of up to 10,000 particles per minute, which is pretty impressive. So let's talk about what causes these particles to grow. So I'm going to show you, this is from research that some of my students did a little while ago, where we were looking at the Hansen solubility parameters to see if we could change the shape of crystals. So the different crystals that we get are all the same chemical species. They're all nitroaniline, okay? But you'll see the dramatic differences in the shapes of the crystals that we get. So let me just back up a little bit and talk to you about how particles crystallize or precipitate out, okay? So when you have a molecule that's dissolved in a solvent, you've got a solvent cage around that molecule. So here's nitroaniline, and the S just is solvent molecules around that molecule. So it's holding that molecule into solution because of the interactions that molecule has with the solvent. And so those of you taken thermodynamics will remember, but if you haven't, think about the different intermolecular attractions that molecules have. You know of hydrogen bonding, right? Anything with like an oxygen or a nitrogen, those lone pairs, the hydrogens can be directed towards those lone pairs, and you can have hydrogen bonding. That's one of the stronger intermolecular attractions if you have those alcohols or amines or carbonyls in a molecule. If you don't have those, the molecule can still be polar, right? It can have kind of a positive in or a negative in, like dichloromethane. You got two chlorines down here, you got two hydrogens up here. That's a positive end of the molecule, it's a negative end at the bottom. It really doesn't hydrogen bond, so that's just polar. And then you have dispersion. So that's like this benzene ring in the middle. It's going to have this huge electron cloud, and that helps interact with the solvent. So D, P, and H, dispersion, polar, and hydrogen bonding, are the different intermolecular attractions that we have that keep things into solution. So when we say like dissolves like, that's what we mean. Things that have similar dispersion, similar polarity, and similar hydrogen bonding will interact really strongly with each other. And that's how we get things to dissolve. So if we have this molecule dissolved in a solvent and we crash it out, let's say we just take this and dump it into water. Well, nitroaniline really doesn't like water. It doesn't really hydrogen bond except for the nitro side. The amine side is planar because those lone pairs are delocalized onto the ring. You could draw all kinds of resonance structures, and so we've got delocalization of those lone pairs. So it's not a very basic molecule, doesn't hydrogen bond well, and so you dump it into water, it's going to form crystals and grow. Now there's a couple of different ways that it can nucleate. Let's say they nucleate with the benzene rings, maybe they stack on top of each other or something like that. And then it can grow. So we have nucleation, the pairing of those molecules. As soon as two molecules get together, we have at least the opportunity to grow into a crystal. So we have nucleation, that's the first step, and then we have growth. They can grow this way, like I'm showing sideways, or they could grow down, right? We could have those NH2s hooked to those nitro groups and grow that way because they have those dipole moments. And so there's always a competition between nucleation and growth. So all of those particle distributions come from this process where the particles have nucleated and grown. And it's very temperature dependent, it's very environmental dependent. So preparing those different particles, powders, distributions, if they're prepared in different ways, you're going to see it in the distribution. And so what I wanted to do with the Hansen solubility parameters is to see if I could control that. So if we have a microcrystal, they typically have different faces. Like in this case, we have a couple of A faces and a B face. So if the solvent favors the B face, let's say we have a hydrogen bonding solvent and the face here on B shows a lot of NH2s or OHs, then the solvent is going to be strongly attracted to B. So that means that the solvent can be pushed away from the A face because it's not as attracted to A. So the A faces are going to grow. So that would produce a plate. So the solvent is stuck to B, and in order to grow B, we'd have to get that solvent out of the way so that other molecules could stick to B. And so if you stabilize the B face, then preferentially, then A would grow. Does that make sense? Because it's easier to move the solvent away from the A face. It doesn't like A as much. So it's a competition between the molecules that are making the crystal and the solvent that's stuck to the faces. So that's the growth mechanism. What if the solvent favors A? Well, now it's stabilizing A and it doesn't want to get out of the way for more molecules to come and grow in those areas. So B would grow and then we would get needles. So in all of these crystals, you have different functional groups, if you want to think of it that way, expressed on the surfaces. So if the surface has a bunch of OH groups and you're going into water, water is going to stabilize the OH face, and whatever the other faces are going to grow because water doesn't care about them. So it can move out of the way and you can get more precipitates to stick to that face. If you do this slowly, you can get perfect crystals. that are suitable for like X-ray diffraction and so on. If you do it fast, you get tiny little crystals. They're still crystals, they're just micro. Okay. And then if the solvent doesn't care about any of these, then you just get the crystal growing in all directions and you get more of a round particle, okay, or a cube in this case. And we showed that we could do all three of these with the same molecule. So nitroaniline produced all three of these crystals, depending upon the solvent that we used. So how did we do it? Well, we looked at the Hansen solubility parameters. First, we determined what nitroaniline's Hansen solubility parameters were, and then we played with the precipitation paths. So this was to see if we could control the macroscopic particle properties, the crystal morphology. Okay. Now this was important to us at Pantex because we were looking at explosives and how the explosives crystallized in this process would change some things about the explosive, how fast it detonated, how tightly it could be pressed. There were a lot of physical properties that depended upon the shape of those crystals. And so I'll go through quickly this Hansen solubility parameter space, okay, and I'll explore what we mean by precipitation paths, okay. So we did this for all three, ortho, meta, and para nitroaniline, okay. So we weighed about between 0.2 and 1 gram of solute into a vial. So we had a bunch of different vials, and we put this similar amount or a known amount of nitroaniline in each vial. So if you want, this is a side trip. If you guys are in the future ever need to determine the solubility of a powder in different solvents, this is a great way to do it. So you get a bunch of different a bunch of different powders and vials. Let's say you have 20 solvents, so you get 20 vials. You weigh out powder in each of those 20 vials, okay? And you get the initial weight of the powders, okay? Then you add solvent drop-wise, and you record the mass, so you know how much solvent you put in. And then you look at it and see when the powder dissolves completely, okay? So you put, let's say it's super soluble. You put 2 drops in there, and it goes completely homogeneous. You can put a whole lot of powder in that. So it's very soluble if it dissolves in 2 drops. If it's not soluble at all, you put 50, 60 drops in there, and it's still got powder. It's insoluble in that solution. So this is what we did. And so these are the different vials. You can see here, this was for 2 nitroaniline. It dissolved in a very little amount of like DMF. This is the amount, and it's perfectly homogeneous. Hexane, we filled this thing all the way up, and you still had powder in the bottom. Absolutely not soluble in hexane. Toluene, the level is up here. You can see if the level of toluene is up here before it goes completely into solution, then it's less soluble in toluene than it is in MEK or in NMP or propylene carbonate, So we had masses of all of these. And so it was a very easy way to determine the solubility of this substance in all of these different solvents. And here's what we did for the 3-nitroaniline and 4-nitroaniline. Look at the propylene carbonate here. It took this much to go homogeneous, and in NMP it took that much. Okay, in toluene it took this much. So you can see it's not very soluble in toluene, not very soluble in propylene carbonate. Hexane is still a powder in the bottom. The hexane was a problem because as the students were doing this, they waited too long, and some of the hexane evaporated. So that's why it's so low. It actually should be a lot higher, but that's okay. So then I'll skim through this. We calculate the distance to each of the solvents in the Hansen solubility parameter space. Okay. And we get this sphere. So this is the Hansen solubility parameters of 4-nitroaniline. And we made a determination. If it was inside this sphere, we said it was a good solvent. So we calculated the distance to all of these different solvents. And we drew this sphere that contained the good solvents and excluded the bad solvents. Like acetonitrile was a bad solvent, ethyl acetate's a bad solvent. This is isopropyl alcohol. It's a bad solvent. So we made some sort of subjective determination as to what we called a good and bad solvent. So the ones that had the smallest volume The very smallest volume, we called those good solvents. The one that had larger volumes, we called bad solvents. And we can draw this sphere. So if we're inside this sphere, we've got a good solvent. If we're outside this sphere, we've got a bad solvent. Now this is nice because I've only used maybe, I think you could count them up, 12 or 13 solvents. But now that I have this sphere, I can go to a table of 10,000 solvents and I can predict which ones are going to be good. Let's say, for instance, which is happening today, the EPA is taking solvents off the market. You can't use this, you can't use that, you can't use that. But if I know the solubility sphere, then I know what solvents I would work to substitute. It also allows us to do blends, okay? And so this is software that can do this. Okay, so if we were to blend acetonitrile and ethyl acetate, it would actually be inside the sphere. So the blend of two bad solvents can be made to give a good solvent. IPA and toluene doesn't go inside the sphere. So it would not, the blends, none of the blends would be a good solvent for that. Although this would be better, it's closer to the sphere, so we would pick that if we had to use those two solvents. About 2 parts IPA and 1 part toluene would be the best possible blend of those two if you could get those two to blend together. And so there's software that does this. I don't know if they, I don't know. We were developing this at the same time. It was kind of a race. So the people that write this software, I know, and they were coming up with this blend optimizer the same time we were here at SAM. I had Brian Loft in the math department do some of the math, and then I had a student write some software for it. And so we were kind of racing against this software developer, and they put it in their software. We have our own that we have to run on a spreadsheet, or we have some Python code too. But they stopped at 3 components, and so we made a 4-component optimizer, and so ours will go up to 4 components. So I'm very happy about that. Yeah. So then let's get to the solvent precipitation. So that now that we know what the properties of the solute are, and we know the good solvents that will dissolve it, and we know some of the less good or bad solvents, we know water's the worst. Water's way up there, and 4-nitroaniline is going to crash out in water and make a really fine, small particle size precipitate. Why is that? Well, because it's so poisonous. You put water into that solution, and the nitroaniline hates water because it doesn't hydrogen bond. And so the growth mechanism, it's not in solution long enough to grow. It just nucleates and crashes out. So you have really small particles because nucleation is really favored when you have such a poison solvent. So we take the good solvent away from those molecules, we start throwing water on there, and the nitroanilines go, I hate water. I'm going to find a partner of nitroaniline, and I'm going to start making a particle, and then the particle just falls out of solution because water doesn't hold it in solution. So you get nucleation and precipitation, and you have no longer any opportunity for growth. Okay. What if we put it instead of straight into water, we put it into toluene? It doesn't like toluene, but it doesn't hate it as much as water. Okay, so we're doing this. So we take a saturated solution of 4-nitroaniline, and we mix just 1 part to 9. So we make a 10% solution into a non-solvent like acetonitrile or methanol or toluene, and then we crash that into water. So this is what we're doing. We're taking this and we're nucleating new crystals and then letting them grow. And so here's what we're doing. We're taking this path 1, crashing it directly into water. That's our reference. So it nucleates a lot, but then they crash out really small particles because it absolutely hates water. Okay. Or path 2, we take this nitroaniline and we put it in a non-solvent like toluene. Okay. And then those green solvent molecules are replaced by non-solvent molecules. So it doesn't really like it, so it starts to nucleate, but it doesn't hate it, so it doesn't crash out yet. So it starts to nucleate, and there's more time for growth. Now, because of the Hansen solubility parameters, you've got some molecules that look like benzene, and so it'll stabilize the benzene face, and they may grow this way. Or you've got other molecules that are polar, and they'll stabilize the nitro and the aniline piece, and the crystal will grow this way. So depending upon where we go in the Hansen solubility space, we can maybe control the faces that grow, and we can get needles or plates or whatever. And then we crash it into water, okay, to just stop the process and dump it out. So we talked about this, depending on what face the solvent favors. So this was our setup, super easy. We had our saturated solution of 4-nitroaniline and DMF. And so then we just took 1 drop off the top of that and mixed it into 9 drops of the non-solvent, like methanol, toluene, and so on. And then we took 1 drop of that, or I think it was 1 mil actually, 1 mil to 9. And then we took 1 mil of that solution and dropped it into 9 mils of water, and we saw an immediate precipitate, and then we filtered that. And this is the work that the students did. So here was our apparatus. And we kind of used the laser. This is a flashlight, but it has a laser in it. So you can kind of see the laser light there. And so we don't see a lot of scattering. And then when we see the precipitate crash out, I thought we might need the laser to see the particles, but no. When it crashed out, it became milky yellow solution. So that's what it looks like when it crashes out of solution. So when we go into the non-solvent, we didn't see a lot of particles. And so we stabilized the nucleation, and we're letting growth happen. We're spinning the stir bar, and we take a mil of that, put it into water, big crash. We have lots of powder then. And then we filtered it. So Buchner funnel, filtered the particle, washed it out with water to get it all through. And the students did great work. It's a lot of tedious work. They did all of those samples with the 4-nitroaniline, the 3-nitroaniline, the 2-nitroaniline. And then when we started looking under the microscope to see what the particle sizes look like, and we see all the microscope slides there. So this is what it looks like in the Hansen solubility parameter space, okay? So this is going straight into water. So here's the nitroaniline in DMF, dimethyl sulfoxide, and dimethyl formamide, and it's going straight to water, and it's exiting its solubility sphere right here. So once you put 1 mil of this solution into water, as soon as the solvent sphere changes and gets outside this solubility sphere, you start to form precipitates. And you can see that the crystals are not well formed because it crashes out so fast. It started to form some needles, but you can see there's lots of irregular shapes here because of the violence of the precipitate. It starts to grow, but then it crashes out as soon as it gets so big that it can't stay in solution anymore. This is also for microscopists. This is an embarrassing slide because I'm not a microscopist yet, still working. I don't have good dispersion of these crystals. So there's lots of overlapped crystals, and that's the thing that makes this slide really bad. I'm using cross polarizers, so that's why the back is black. So the polarizers are crossed so that light that doesn't go through a particle is black. Lights that go through the particle is rotated, and then I can see through the analysis polarizer. Okay, so here's the precipitation path where we went into methanol. So we went out, so 1 mil of DMF particle solution went into methanol, to 9 mils of methanol, and then 1 mil of this solution to 9 mils of water, and then it was crashed out when we did that. And look at the crystals, they're much more perfect. We've got nice needles, some pretty large needles. You see very pure colors, which means that the crystals are crystalline. They're not irregular. They're not amorphous. So we're getting much more crystallinity, which means we're getting more perfect growth. So that growth mechanism is happening slower in methanol, and we're probably stabilizing the certain faces in that crystal. Here's when we went into ethanol, similar. Although with ethanol, we start to see some plates. So here's a plate here in ethanol, okay? Again, some good colors, so we're seeing some more pure crystals. And then here we're going into acetonitrile and then to water. So we're exiting that solubility sphere in a different direction, and we're seeing even skinnier crystals. So the length to the width ratio has increased by picking a different path out here. So we're really stabilizing one of those polar faces and causing the other faces to grow. Okay. And then here we're going into acetonitrile, again another polar solvent, very little, acetone, a polar solvent, and we're getting stabilized faces that produce plates. So here's plates. We see lots of plates. So we're changing the length to width ratio. We're changing the crystallinity of this precipitates. And then when we go to ethyl acetate, their crystals are not as pure. Okay, so we're losing some of that polarity. We're losing some of the stability of the faces. And then when we go to toluene, it's terrible. We got gravel with toluene. It's so insoluble in toluene, we get really rapid nucleation and almost no growth. So we're not stabilizing any of the faces. Okay, and then we see this one, it's almost a picker, not quite, but we see this one large crystal here. And remember, when we had a polar solvent, we were getting these needles, okay? And toluene's not polar at all. So how is it that we got this one needle? I did this particular one, and that needle grew on the side of the beaker. So the side of the beaker is playing a role too. Now this is important because we almost never think about the container. But the Hansen solubility parameters apply to everything. They apply to the solute, they apply to the solvent, they apply to the stir bar, they apply to the walls of the container. And sometimes it matters. In fact, we're starting to learn this. I mean, some of the gourmet cooks are buying copper cookware because it behaves differently than steel and aluminum. And it's this effect here. At my former place of work where we were trying to synthesize certain explosives, they upgraded the facility from this old way they did it in World War II with a big copper kettle. They went to a stainless steel vessel because stainless steel is better. And all of a sudden they couldn't get the right crystal shapes and so on. And they went back to copper and it worked. So it was an effect of the container that was giving them the distribution that they wanted. And that was the effect here with toluene. This big old crystal grew on the side of the glass, and I remember seeing it. I was trying to wash it down, and so the glass surface stabilized that crystal and gave us a needle, as opposed to all the gravel. You see all of this other nasty stuff. And then into propylene carbonate, also gravel. So we see that the polar side with low dispersion is the best for growing some of these crystals. Now, these are all of the precipitation paths, and just a sort of a quick cursory glance. You see, these right here are definitely more like gravel. And this is definitely a mixed bag here, the acetone and so on. But it looks like we got needles over here, like in that. Let's see. Acetone and ethanol, more like needles. And then for water, straight to water, we had irregular. Now, just forensically, I want to point out that this is the same chemical structure, right? So if we did a chemical analysis of these different samples, we would get the same answer. Same FTIR, same mass spec, all of that. So the chemical properties are not any different no matter which path we had. Now, okay, maybe we could get residual solvent. So like maybe from this one we would see residual toluene, and maybe from this one we would see residual acetone. And so a residual solvent analysis might be able to reveal that these were processed differently. So that might be a chemical signature that we can say this powder and this powder are different. They have a different origin. Okay, but the particle size, a simple micrograph, looking at it under a microscope, could tell you that this one here is different than that one. even though they're the same chemical signature. And so it's always good to look at the particles and maybe even get a count or a distribution. So I went through and did this by hand, did the length to width ratio, and converted to microns from pixels, and did length to width ratio, and did a cross-sectional area, meaning length times width, and did particle size distributions based on these things. And so I got huge error bars, okay, but still I didn't see any conclusive evidence that the polar parameter created a trend, okay. It's hard to say because of the error bars, right? And then dispersion, really, because of the error bars, didn't see much of a trend. But with hydrogen bonding, there was a possible trend, like a 68% of the scatter in the data could be determined using the hydrogen bonding parameter. Now, why are my error bars so tall? We'll talk in a second. So this is doing those same kinds of cumulative fractions, and so these are the data points that I have. And we have needle type structures from acetone, and let's see, this was methanol. So acetone and methanol were needles, and then we had more like gravel from toluene and propylene carbonate and so on. And then if you'll notice the acetone definitely might be bimodal because you got a steep part here and you got a steep part here. Okay, so these are the small particles, and then these are the sizes of the needles that we have. Now, the problems with my analysis were that I counted about 200 particles per system. Absolutely tedious. I think I asked you about counting cells, right? And y'all were just counting types of cells. You weren't measuring length to width ratios. And so if it's tedious to count cells, imagine how tedious it is to count particles. So I did this by hand because I don't have the analysis system to characterize these things automatically. So of all of those little petri dishes, all I counted was 200 particles roughly for each of those petri dishes, which is not near enough. That's why the error bars on my analysis are absolutely huge. So, but I did sort of satisfy what I was after. Is there a different particle shape depending upon these precipitation paths? And the answer to that is absolutely there is. Okay, these are the students that did the work. Katie's got her PhD now. John, I don't know where Steve is, but John's working for Baker Hughes. Carl's working for, let's see, he went to work for GE Oil and Gas. Now they've changed company names twice now. I forget the new one. And then Derek also went into oil and gas up in Pennsylvania. So doing it by hand is incredibly tedious. So now they make systems that will do this for you. I talked about the sort of the cascade particles flowing in front of a camera. Here, this analyzes filter disks. So if you can get the particles dispersed on your filtration disk, you just put it in this microscope and it'll do the counting for you. So let me show you this system. This is made for automotive particles, and so they're looking at particles that they wash off the parts. So let's say they make fuel lines, and you don't want any particles in the fuel line because you don't want those abrasive particles getting into your fuel injectors. They'll clog your fuel injectors. So they have really stringent requirements on particles in fuel line systems and certain automotive components, because one 200 micron particle can clog a fuel injector and you're done. So they have like no particles above this certain range, a few particles to pass the test, maybe 5 or fewer particles in the 100 micron or less range, and so on. So they have really stringent requirements. And so they've automated this because you can imagine on an assembly line where they're making these parts, I don't know how frequently, but 100 a month or 1,000 a month, they need to automate this process. So this is, okay, let's go. Where's the video? So on the left is an optical microscope, and on the right is a scanning electron microscope. So this is the little filter disc that you take out of this washing station, and your particles are dispersed on the filter disc. You tell the computer where the disc is located. So a couple of little reference can put it in the SEM, and the computer keeps track of the location of every particle. So it can go to that particle and do a scanning electron micrograph to get a better picture of the shape, the size, but more importantly, it can give you the composition. These are made again for automotive analysis, but it's just important to know, even in forensics, that these kinds of systems exist and that you can go out there and you can buy microscopes that will scan the whole disk and analyze every particle that it sees. And it's correlated so that you can take it to the scanning electron microscope and you don't have to find that particle with X and Y. That you can stick it in there and the computer knows where that particle is. So let me show you some of the particles that it found. So like in this case, it finds this particle. This is the optical image you can see up here. Here was a fiber. There's a particle. There's a bunch of different particles. It keeps track of every particle here. This is particle 81 out of 81 that it found on this disk. We put it in the SEM, and here's the optical image of the particle, and here's the scanning electron micrograph of the particle. But this is the beautiful thing right here. This is the energy dispersive spectrum of that particle. So they blast it with electrons and they look at the X-rays that come off and they see an X-ray for chromium and 2 for iron. And again, you have the carbon here, the oxygen, the fluorine. Carbon's everywhere, so you really can't say much about it from that, but you definitely see carbon. What do you know about this particle if you see iron and chromium? Well, iron, that's iron's the metal. So this is a metal particle, okay? But the chromium indicates it's a steel of some sort. And so they alloy iron with carbon. But again, you can't really depend much on the carbon signal because there's carbon everywhere. But the chromium indicates that that's steel. So they put chromium in there to keep the iron from rusting. So they mix iron with carbon, high and low amounts of carbon, and they put in chromium, like chrome plating. You can have nice chrome plating, it doesn't rust. They put chromium in with iron and they mix it together, and then they do what's called pickling. They can dissolve that in acid a little bit. So they put it in acid, and that dissolves the iron off the surface and leaves behind chrome. So iron preferentially dissolves in the acid, and so then you've enriched the surface with chromium. You're not plating it with chromium, you're dissolving the outer layer of iron away, and you're making stainless steel that way. And so this is a stainless steel or steel particle, and it's going to be abrasive. So if that's in your fuel line, you're probably failing the test because you don't want that particle to get into your fuel injectors. Okay, but you've machined these parts, so there's particles of steel everywhere, and so trying to clean those off, you clean them, then you do this test to see if they've been cleaned well. What about this one? See, it's a little bit of a yellow color in the optical, so it might suggest a copper or a brass, and sure enough, you see here copper. Maybe a little zinc, okay? And here we, hit it again with the X-rays, and you get zinc, more zinc. And so what is copper and zinc? That's brass. So this is a brass particle. And again, it's done automatically for you. So if in a forensic situation, if you could do this, you could hit those particles, you could say, silicon oxide, or an aluminum oxide, maybe it's a clay. It's zinc and copper, it's a brass particle. So this is really great that you can do this particle analysis. Here's some more chromium and iron, so that's a steel particle. What if you saw like silicon and again, carbon and nitrogen might be a little iffy, but still, you saw silicon, it's probably a silicon carbide, okay? Or or titanium nitride or so on. So here's the different SEM analysis. You could zinc chromium, zinc manganese, steel, different types of steel, silicon particles. Here's silicon nitride, here's aluminum oxide. There's different sort of classifications of aluminum rich, zinc rich, and so on. And this is, notice you've got one brass particle, three copper rich particles, an aluminum particle. Here's high alloyed steel. Here's one, and this is the size. So this was this aluminum rich particle was in the 200 to 400 micron size. Let's see, where were here's the brass and copper rich alloys in the 200 to 600 micron range. Here, this steel particle, there were two in the 200 range and one in the 150 to 200 range. We don't have any huge particles. There's no pickers, okay? But we've got some in the 200 micron range, which, again, I don't know the automotive spec perfectly, but if it's a 200 micron particle, you're getting close to failing because that's something that could clog. If you have a super small particle, you might pass because it might go through the fuel injector or the small components in the transmission. Here's the particle size distributions. We have these different classifications of sizes of particles, okay, and here's their count and so on. So, and here's just, again, some more of the SEMs. Here's the visual picture. Here's the SEM. So conclusions that you know, the particle size distribution has incredible information in it, and I think it's definitely forensically relevant because you have a question and a known sample, and you're wanting to see, are they the same or the different? You know, so you get, again, something on the shoe, that's your question thing. You go to the site, you take a sample, that's your known, do these match or not? They might match chemically, but if the particle size distribution is completely different, then they're not a match. And so if you don't look at that kind of information, then you might make a wrong comparison between the known and the questioned objects. We're done. So was it a good semester? You guys happy? Okay, good. All right. Evaluations are open. No. The final report is due on Saturday, but you can turn it in early. So if you're ready to go and you want to go ahead and just like say it's done on Tuesday or whatever, that's okay. I know this instructions say it has to go through Friday to turn in, but if you guys are ready, go ahead. You can turn it in early to get on to the next thing and start studying. So sound good? Okay, great.